Hello everyone and welcome back to the channel CSAI TTL. Today we are diving deep into the linked list topology, cycle detection and repair protocols. Before I get into that, I want to introduce our companion website, which is bitbytoken.com. This website we have prepared for people who want to get more in depth in system design and understand the various core concepts related to software engineering, data engineering, and let me just break it out. Yeah. So it has components for core software engineering, data engineering, machine learning, and AI engineering. Each of these are actually further, we have several fundamentals listed for those corresponding to specific spaces, and then we have sample solutions related to these. So, for example, each of these are pretty comprehensive. We can look into details in these. Um, we can look at various functional requirement for them, non-functional, again moving on with the data models. We try to provide as much architecture detail possible along with different data models. um, we also try to provide the sequence diagrams. Please do have a look at this site, provide your comments how we can make it better for better understanding, and let's jump on to our topic now, which is so if you're ready to master detecting and fixing cycles in your linked list, please do remember to like, share, and subscribe to the channel for more engineering insights. Now that we have all the things out of the way, let's move on. On this page, we see a detailed breakdown of a linked list node. Each node consists of a data payload, which is application-specific data, here shown as 4 bytes. Crucially, it also contains a next pointer, which is an 8-byte, 64-bit address reference, making it a platform dependent. The total node width is 12 bytes, encompassing both the data and the pointer. Our objective is to detect and resolve structural cycles in linear data structure without increasing memory footprint. The method that we're going to use is differential pointer velocity, specifically Floyd cycle finding algorithm, a brilliant technique by Robert Floyd. This approach, often called as the tortoise and hare, offers O(n) time complexity and O(n) space complexity, which is optimal for cycle detection. This foundational understanding is key to navigating the cycle risk inherent in dynamic memory structure. Let's start by understanding the structural failure scenario, the infinite loop. In a perfectly linear system, termination is guaranteed by a null pointer at the end. However, as shown in this diagram, a structural failure, back edge, can occur when a node deep within the list points back to an earlier node, forming a sort of a cycle. This creates a trap, a recursive geometric flaw. Once a traversal enters this infinite path, a standard iteration algorithm will never terminate, causing the system to hang. The cycle radius highlights how these nodes are trapped in a loop, making them inaccessible in a linear fashion after the loop is entered. To tackle this problem, we have two main approaches. Approach A, the memory hog or the hash set, involves storing references to every node you visit in a hash set. If you encounter a node whose reference is already in the hash set, you have found a cycle. While effective, this approach has a space complexity of O(n), meaning the memory usage grows with the number of nodes. This is often unacceptable for a large list, as you're trading performance for storage. Approach B is the kinetic solution, which is the Floyd solution, offers a much more elegant solution. It trades storage for physics using two pointers with differential velocities, v and 2v. This method achieves a space complexity of O(n), making it optimal as it uses a constant amount of extra memory regardless of the list size. Let's dive into the physics of detection using an analogy, the foggy track. Imagine two runners on a track. The jogger moves at a velocity v and the sprinter moves at a velocity 2v. If the track is perfectly straight, the sprinter leaves the jogger behind forever. They'll never meet. However, if the track is circular, the sprinter must eventually lap the jogger. Because the sprinter is moving twice as fast, they will be inevitably catch up and collide. This collision is our signal. It tells us that a cycle exists in our linked list. The fog represents the unknown length of the track or the cycle, but the physics guarantee a meeting point. Continuing with the physics of detection, let's apply this to our linked list pointers. The mechanism relies on differential velocity. We use two pointers. One, a slow pointer. This pointer advances one node, which is the next, at a time. Two, fast pointer. This pointer advances two nodes next dot next at a time. As these pointers move through the list, if a cycle exists, the gap closes by one node per step. The steady closing of the gap ensures that if a cycle is present, the fast pointer will eventually catch the slow pointer. This brings us to phase 1, the guaranteed convergence. Once both the fast and the slow pointers are inside the cycle, the fast pointer will inevitably chase and catch the slow pointer. As we established, convergence is mathematically inevitable. The diagram illustrates this in three steps. Enter, where both pointers enter the cycle with a large distance between them. Chase, where the distance closing as the fast pointer gains on the slow. And finally impact, where they meet at the collision point M. The key insight remains. Gap closes by one node per step, ensuring their eventual meeting. To understand the cycle structure, we delve into the topology geometry, defining the variables. Once we have detected a collision at meeting point M, we need to locate the actual start of the cycle. To do this, we define three key distances. X approach is the distance from head of the list to the start of the cycle. Y travel to collision is the distance from the start of the cycle to the meeting point M. And Z, which is the remaining loop, is the distance from the meeting point M back to the start of the cycle, completing the entire loop. These variables are crucial for the next step of locating the cycle's beginning. Now for the derivation that underpins Floyd's algorithm. We use the distances we just defined and the velocity constraint. Number 1. The distance slow pointer travel is x plus y 2. The distance with fast pointer travels is x plus y plus n y plus z plus y, where n represents the number of laps the fast pointer completes within the cycle. The velocity constraint states fast equals 2 times slow. By substituting the and assuming n equals 1 for simplicity, we get to 2 times x plus y equals x plus 2y plus z. And simplifying this further by subtracting x plus 2y from both sides, we arrive at the profound geometric truth x equals z. This means the distance from the head to start of the cycle x equals the distance from meeting point to start of the cycle z. This equality is the key to identifying the cycle's beginning. This mathematical truth leads us to phase 2, the reset maneuver. By exploiting x equals z, we can precisely locate the cycle start. The maneuver involves three steps. 1. Reset slow to head. We move the slow pointer back to the beginning of the entire list. 2. Keep fast at meeting point. The fast pointer remains at the collision point M. 3. Move both at 1x speed. Now both pointers advance one node at a time. Because x equals z, they'll collide at the cycle start. The second collision uniquely identifies the exact entry point of the loop within the linked list. To grasp the elegance of this, consider the intuition, the sync point. Think of this process as a synchronization. The fast pointer has lapped the slow pointer such that the remaining distance z from the meeting point back to the cycle start perfectly match the approaching distance x from the head of the cycle start. The sync line visually connects the head, the meeting point, and the cycle start, illustrating the critical geometric relationship. When the two pointers, one from the head and one from the meeting point, converge, they pinpoint the destination slash cycle start node. Once the cycle start is identified, we proceed to phase 3, which is the structural repair. The restoration protocol is to break the loop and to restore this list to a linear structure. We do this by traversing the loop to find the predecessor of the cycle start node. This node is typically referred to as the loop end. Once found, We sever the backlink by setting its dot next equals none. This effectively grounds or earths the loop, turning the infinite cycle into a properly terminated linear list. The diagram shows the from loop end arrow being severed, pointing to null, thus restoring linearity. Here are the implementation specs in a Python code snippet for detect and remove the head. The algorithm is broken down into three phases. Phase 1, detect. This phase uses the while loop with fast and slow pointers to detect intersection. If they meet, a cycle exists. Phase 2, locate, which resets the slow pointer to the head and moves both pointers at 1x speed until they meet again, allowing us to find entrance to the cycle. Finally, phase 3 is repair, which traverses from the fast pointer until its next node is the slow pointer, which is the cycle start, then sets fast.next equals none to sever the link. The overall complexity is time O(n) and space O(1), making this an efficient and optimal solution. We must also consider robustness check and edge cases. Floyd's algorithm is resilient and handles various scenarios. For an empty single node list, the pointers will never enter the while loop for detection, resulting in safe termination. 2. In a case of cycle at head, where the head itself is part of the loop, the algorithm still works. The x equals 0, so the pointer meets at the head and the logic holds. Even for a case self loop, where a single node points to itself, a cycle length of equals 1, the fast and slow pointers will collide on that node and the logic holds. These checks confirm the algorithm's reliability. To summarize, here is the operational summary of Floyd's cycle finding algorithm. It follows a clear sequence of steps. First, initialize the tortoise and hare pointers. Second, detect by finding the meeting point where the fast and slow pointers collide. Third, reset the slow pointer to head. Fourth, locate the cycle start by marching both pointers at the same speed until they collide again. Finally, repair the list by breaking the link at the end of the cycle. This entire sequence represents algorithm Floyd cycle finding with a timeless and elegant solution. In the soul of the machine, we truly appreciate the elegance of this algorithm. We use the problem itself, the cycle, to find the solution. By deeply understanding the relative velocity of pointers, we were able to transform what initially appears to be a fatal error into a calculated geometric proof. The result is a verified linear list. This is a powerful demonstration of how theoretical insight can lead to a practical, efficient solutions in computer science. What are your thoughts on the Floyd's algorithm? Or perhaps another favorite cycle detection method? Share your comments below and do not forget to like, share and subscribe for more deep dives into the complex engineering topics. Thanks for watching. Until next time. Bye.